We're now going to kind of get into the meat of this lesson, and that's graphing exponential functions. And there are really only two different outcomes. You can have an exponential growth model that is an increasing function. So if you notice everywhere on this x, as x is getting bigger, these y values are also getting bigger. It's increasing. Or you can have an exponential decay model, meaning it's a decreasing function. And same thing, but opposite, right? As these x's are getting bigger, these y values are getting smaller. Most of our polynomials were not all increasing or all decreasing because they were, going up and down. And even your parabola was decreasing over here and then increasing up here, right? So growth is all increasing, decay is all decreasing. So let's try graphing some of these in most basic form here. Okay, and so we're going to start with example 4 in this video. And we want to graph y equals 2 to the x power. So that's as basic as this can get. So let's get some x and y values. You can just plug in values into x and solve for y, or use your calculator. If I put in 2 to the x power, 1, I can go zoom 6 to see what this looks like. So I can see from this, is it increasing or decreasing? It is increasing here. But let's get some values. So if I go to table right here, so second graph, I can get some values. And I'm going to start right here at -2 and go to 3. So -2 to 3. And at -2, I have 0.25, so that's 1/4. At -1, I have 0.5, that's 1/2. And then we have 1, 2, 4, and 8. So I went ahead and already plotted these, so pause your video and plot those. But before you plot them, let's talk about what's happening here. Okay, so I hope you had time to pause your video. We have plotted all 6 of these ordered pairs here. Before I connect, we have an asymptote on this graph. Where would this asymptote be here? Now, when I look at these values here, you can even look at them in this graph, and I'll do that here in a second. As these x's are getting bigger, what's happening to these numbers every time? It's going from 1/4 to 1/2, from 1/2 to 1 to 2 to 4 to 8. Everything's doubling. And why is that? That's because that's what my growth factor or my base is. Because my base is 2, these are all going to increase by doubling. So if I was to go this opposite way, these are all getting cut in half. And you can see here, these numbers are getting smaller and smaller and smaller to where it's in scientific notation because they're getting closer and closer to 0. So we have a horizontal asymptote right here on our x-axis. So mine looks a little bit more like it's under, but I can't really do it on top of, or otherwise you won't be able to see it. So I have a horizontal asymptote right here at y equals 0. So my asymptote is horizontal at y equals 0. So when I connect these points and I go this way, I want to make sure I don't go down below that asymptote, below that x-axis. So we're going to stay just right there above it. Okay, so there's my graph. So now let's answer the rest of these questions. What's my domain? We go from left to right. We go arrow to arrow. So my domain is -infinity to infinity, which we talked about a couple lessons ago. That my domain is always going to be all real numbers anytime I have an exponential. Now my range, as I go from the bottom to the top, the first thing we hit is this asymptote at 0, which means it's never going to touch 0. So we have parentheses 0, and then it's going to keep going up forever to infinity. Because I have a horizontal asymptote on my x-axis, I have no x-intercepts. But then my y-intercept is where? At 0, 1. Okay, so let's kind of look how this can vary as the base of this changes. So we said here, because I have a base of 2, these numbers here are doubling. So when I have a base of 3, what's going to happen to my graph? Well, let's pull it up. Okay, here's 2 to the x that we just graphed. Now, when I have 3 to the x, instead of those y values doubling, they're going to triple. So what's that going to do to my graph? Well, now right here in blue, it's going to increase 3 times as fast. When I have 4 to the x power, it's going to increase 4 times the speed. 5 to the x, 6 to the x, and 7 to the x. The bigger this base is, the quicker this thing is going to shoot up right here once we go up. Now, there are several things that we have in common, no matter what that base is. Pause the video if you want some time to look at what these have in common. Okay, hopefully you have an answer. You've had time to pause. They have 2 big things in common here. First off, they all have an x-intercept right here. Nope, a y-intercept right here at 0, 1. Why? Anytime I put 0 in here, that was one of our exponential rules, or I think it called it a law, was anything to the 0 power is 1. So they're all crossing right here at 0, 1. The other thing they all have in common is they have the same horizontal asymptote right here at y equals 0. Now, I stated in the previous video as well that your base cannot equal 1 because we have a property that says 1 to any power is always going to equal what? 1. So if I have 1 to the x power, that is linear because no matter what you put in for x, it's just going to always equal 1. So if you want this graph to get more shallow, you would have to do things like a maybe 1.5 to the x power. So here's my green line that makes it not increase as quickly. 1.25 to the x power. Gets even shallower. 1.1 to the x power. Almost looks like a line. It's increasing so slowly. Okay, so it can get close to 1, but it cannot equal 1 because that's just a straight horizontal line. So coming back to this right here, my graph is always going to be increasing when my base is greater than 1.